Okay, let's see. I'm seeing I got n log n over n minus log n is the break-even point, so it would depend on the length of the data in order to figure out how many times. Sure, yeah, I mean, but yeah, I mean, that's fine. What do you think? Depends on the length of the data. I'm not sure about that. In a sense, yeah, I mean, if I were to ask, yeah. But you can give your answer in terms of the length of the data, so that's fine. I'm trying to think. Uh, Grant, can you walk us through what you did to get there? N log n over n minus log n.
Yeah, can you hear me?
Yeah.
So I can't attest to whether this is correct or not, but what I did
Sure.
was set the linear search and binary search equal to each other. So I started with like nx equals log n x plus n log n. And I guess for me, x is the number of times that you would um, have to search in the list for them to equal each other.
Sorry. So it's like this, or did I miss it?
Um, nx equals n log n. Not quite. On the right side,
Mm-hmm.
I have log n, log of n times x,
Uh huh.
and then plus n log n. Because it's like a single sort that you only have to do. The right side is for like sorting and then doing a binary search. So the first term is multiplied by like the total number of searches. The right side
Mm-hmm.
is just the constant, right? And then all I did was solve for x,
Mm-hmm.
like just using algebra, and then I came to the solution I put in the chat: n log n over n minus log n.
Yeah, great. I think that works. That's not the well. Yeah, this is probably a good way of doing it to get down to the right form. Let me make some notes here. So here, this x. This is the number of times searching. Um, this is the binary search. This is the sorting, only done once. And this is the linear search. Yeah, I think that's a really good way of framing it. That's the equation that I would have sort of come up with. Um, okay, very good. So, yeah, now if we wanted to, so first of all, let me explain this formula again. Now, this is the break-even point. Okay? So for example, well, let me go through each of these parts again. This is how long it would take to do a linear search X number of times. This is the amount of time it would take to do a binary search for the same number X of times. But you need to sort the data before you can do your binary searches. Okay, so those are these three parts. Great. Let's see, as far as the algebra, we can solve for x. Oh, first of all, let's also go through a couple quick examples, just to make sure, like sanity check stuff. This is good to do. What happens when x equals 1? Right, so we're only searching one time. In this case, for the linear search, we'd get n, right? And for the binary search, we'd get log n plus n log n. All right, so here, when x equals 1, then we get the linear search taking time n, and then we get the binary search being log n plus n log n. Now, of course, these are not equal to each other. Okay, this is bigger because, I mean, whatever n is, here you're multiplying n by log n. So clearly these are not equal. But if you make n, I don't know, like let's say 1 billion and 1 billion, maybe at this point it's like this. I'm sorry, it's like this. Or if you multiply this by 1 billion and then you multiply that by 1 billion, so you're searching 1 billion times, maybe then there's like, yeah, there's like a changeover. Okay, so whatever. Good sanity check. All right. So we can get x on both sides. That'll be nx minus log n x. I'm going to put x in the beginning. I'll keep it, whatever. Nx times log n of x. Put that in parentheses. Equals n log n. So we can divide both sides by x, or actually, yeah, whatever, divide both sides by x, do this, then you get n minus log n equals n log n over x. Let's get rid of those. By the way, this arrow just means implies. Okay, so this equation, if this is true, it implies that this is also true, which implies that this is also true, and blah. Okay, let me give myself a little bit more room. Well, now I'm just going to multiply by x again, and then divide by this. So if you do that, then this implies that x equals, let's see, n log n over n minus log n. Okay, so that is the sort of exact answer. Okay. But one thing that I think it's good to have whenever you're doing stuff like this is to try to have it feel more intuitive, I guess. So for example, n log n over n minus log n, I don't really have a good feeling for what that is. For what values of n is this number, and like I have to plug them into a calculator, and I just don't have a good feeling for it. So a kind of quick way to come up with an estimation for this, and it's not exactly right, but it's close enough, is to look at this equation again and figure out roughly for what value of x are these going to be about the same. And I would say plug in log of n. So here, if we make x equal to log n, right, x equals log n, then here we have an n log n, and here we have an n log n plus log squared of n. So log squared of n is like plus something extra. But this is basically the breakpoint, is log n. It's like log n plus a little bit. Okay, the plus a little bit you could figure out from playing around with that, or I don't know, doing other algebra stuff. But just as like a back of the envelope kind of calculation, the first thing is to come up with this formula, which, yeah, is perfect. And anyway, yeah, if you say that x is roughly log n, then it's about right. So what that means is, for example, if you have this much data, 2 to the 1,000, which is like a lot of data, whatever, these things don't matter. The point is to have a feeling for this, okay? So if you have a really long list, then the logarithm of this is the number 1,000. So for however much data you have, if you're going to be doing like however much data that is, take the logarithm of it, and that'll be about how many searches it'll pay off to do to sort your data first. So in this case, if you have a gigantic amount of data, then if you're doing a search about 1,000 times, sort your data first. You'll be better off that way. So it's not so many searches, especially like for a database. That's mainly what you're doing with it. I mean, 1,000 searches is like nothing. Yeah. Let's see. Yeah, so you don't need to know the exact answers on these things, but I do think it's useful to know that, yeah, it's generally worth it to sort your data first. Like you'll benefit from that. And then you can kind of give a little bit of a hand-wavy explanation. If you like, you can, and there's nothing wrong with this, get, the exact kind of breakpoint and give, I don't know, you need to do 1,304 searches in this case. But, you could also say, I don't know, if you're doing like a couple hundred, couple thousand searches, yeah, it's probably better to sort. Okay. Let's see, I have some questions. Yeah, right. Yeah, so that's, like I said, it's just an estimate. And for me, like it's fine. Like, yeah, you can get the exact answer, but one thing that I think is really beneficial is to make things kind of internal. And usually that, for me anyway, is just kind of rounding stuff off. Like +1, -1, like whatever. It's more about the concept. If it really matters, then great, you can go through the longer work. But more important to just have like an idea of what's happening. Okay. Oh, by the way, there was another student last class who was asking sort of how much they should be retaining, I guess, from these lectures, or like what is it that that you really have to know from these things. That'll be a good place to start, actually. So I do go over more detail in lectures than is necessary. Oftentimes, it's because I do like to be a little bit more precise, especially for students who are interested in these kinds of details. But more importantly, is I think for you guys to have like a good basically understanding of things. I mean, you don't have to get down necessarily into like the nitty gritty kind of stuff, but don't like, if you're getting like the main picture, that's okay. So for that, for example, what are files? So here, no, like what's a kilobyte? What's a megabyte? What's a gigabyte? Maybe a petabyte. Terabyte comes first. Terabyte. These, I mean, really, it's just these are okay. I mean, because like that's most of the realm of data that you'll probably be working with. But it is good to blow things up and think about, because this is actually, I mean, like petabyte data is here, and we're working with it, but you're gonna have to be at like a big company or the government or something to be dealing with that. In any case, knowing like sort of what that is, um, uh, how are files stored? We're not there yet. We actually have to get back to this. For data structures, know what a linear, know what an array is, and know a binary tree. We will be discussing the binary tree today. That'll probably take up the rest of class. If not, then I have some other cool stuff we can talk about. For algorithms, know a linear search, and binary search. And know that a binary search takes time log n, and know that a linear search takes time n. And I would also ask for, if you don't have a feeling for what a logarithm is, work on that. Like, take some time and go through some examples. Actually, when we talk about the binary tree, this is it's a nice new perspective on a logarithm that's kind of graphical. So in any case, yeah, like having, well, and I don't know, you guys are in business and school and stuff, so knowing exponents and logarithms are probably good for you anyway. Hardware, haven't gotten enough there to talk about it. But so far, for these lectures, if you know like these sizes of files, and you don't have to know necessarily exactly, you can figure it out, right? If you know what the order is, like first it's kilobyte, then it's megabyte, then it's gigabyte, then terabyte. Like if you know the order that they go in, and that each one is 1,000 times bigger than the previous one, that's fine. Like again, it doesn't have to be 1,024 or anything like this. If you know that it, whatever, like, fine. Good. Any other questions before we get back to talking about binary trees? No? Okay. So, again, when I say binary tree, what I mean is what other people might call a binary search tree. I don't like calling this a binary search tree, although I kind of get the argument for why people make that kind of distinction. For me, that seems like it's confusing things. One is a data structure, another is an algorithm. A binary search is an algorithm. A binary tree is a data structure. And you can do many different algorithms on the same data structure. Like we saw with the array. You can store data in an array, and you can do a linear search, one by one, that's fine. Or you can sort your data in the array, and then do a binary search. So same data structure, still an array, but you can do many algorithms on it. In fact, those are three: linear search, sorting, binary search. You can do all three of those. They should, I think, be separate concepts. A data structure is different than an algorithm. Okay, so whatever. When I say binary trees, I mean binary search trees. All right. So here, this is just vocabulary, okay? This is just so that you know when I use words, what do I mean? We'll kind of go through these in somewhat of an order. So first, all trees, binary trees included, but all trees, have a single root. Okay, that's the very top node. And everything starts at the root. From the root, you go deeper and deeper into the tree. And when I say deeper, I mean you go from the top to the bottom. So you start at the top of the tree, and then you move down level by level the tree. Sometimes you can go back up and do stuff, but whatever. In general, this is the way to think about it. The root is one node at the top, and then somehow you go down the tree, and you take like one path. So there's one path where first I go right, then I go left. That's one path down the tree. Another path down the tree is to go left and then left. Okay, that's another path through the tree. Paths always start at the top and move down. The only other nodes that have a special name are the leaves. In this tree, these are the leaves. Let me get rid of the root now. So the leaves of the tree are the nodes with no children. Okay? It doesn't matter where they are at in the tree. If it's a node with no children, it is a leaf. Okay. Great. Oh yeah, nodes are connected by edges, fine. There is, an array is measured in length, right? What's the length of the array? This array is 10 long, or it's 40 long. You know, it has 40 different places to put stuff. When you talk about arrays, you're measuring them in terms of their length. For trees, you measure them in terms of their depth. Okay? So this is depth. Okay, the depth of this tree is 4 because it has 1, 2, 3, 4 levels. Okay? That's also the length of the longest path, if you like thinking of it that way. So from the root, what's the furthest down you can go? How many steps is that, or how many hops? That's the depth of the tree. And that's the thing that you care about when you're describing trees, is what the depth of them are. So for arrays, you care about length. For trees, you care about depth. So I would call this a tree of depth 4. And if I were to describe the levels, I would start with the top level. I'll call that number 0. And then the next level, level 1, then the next level, level 2, and then level 3. So while I'll refer to these levels as level 0, 1, 2, and 3, I'm talking about a depth 4 tree. Now that being said, I don't care if you want to call it level 1 instead of level 0. That way, you know, the number of the level or the layer is the same as the depth that you're at. Fine. This is just starting with 0 has some other properties that can kind of be nice, but it doesn't matter. Okay, like this +1, -1 thing. You prefer doing it this way. I don't care, but just be consistent. Okay. Right. Okay. Now, the other property of the binary search tree, or the binary tree in my opinion, is that for every node, there's going to be a value, and anything to the left of that must be smaller values. And any of the right children, or any children that are to the right of you, have to be of a greater number. Okay, so this is a very important property of the tree. So I ended last class by going over some examples of valid binary trees. Each of these are valid binary trees. Any node that you look at, everything to its left is smaller and everything to the right is bigger. So here, like this number 5, everything here is smaller than 5. Everything here is bigger than 5. Right. Okay. Any questions about that? Is branch the same as an edge? A branch can be longer. So an edge is a branch, but a branch isn't necessarily an edge. So for example, on this tree on the lower right, this is an edge that I'm drawing in purple. Now in green, that's a branch, but this is also a branch, right? This green line. So a branch can be longer. This is not an edge. This branch is made up of 2 edges, but you can have a branch with a single edge. So this is also a branch. Like you could call that a branch, but yeah, branches are more than edges, although they're composed of edges. Great. Okay, any other questions? No. Okay. I'm going to draw a couple of trees, and you guys can just type in the chat if you like, if it is a valid binary tree or not a valid binary tree. Okay, let's start simple. How about this? Okay, good. Yes, that's a valid tree. Good. How about, let's do, oh, actually, let's just do that. Is this, let me clear this. There. Okay, is this a valid tree? Valid. Okay, how about this? Clear. Okay, good. This is also valid, that's right. How about this? Let me clear. Okay, good. So some mixed responses, but this is an example. This is not a valid tree. It is true. This is okay. But these are the two nodes that are problematic. Okay, everything to the right of 10 has to be has to be larger than 10, and 9 is not. So 9 causes a problem not for 12, but 9 causes a problem for 10 with its location. Okay. Any questions about that? Okay. No. How about that? Yeah. Okay. So this is valid. And sorry, I see a question got buried. What if the 9 branch extends left of the 10? Well, not exactly sure how to interpret it. Let me give a couple of different options. If we got rid of the 4 and put the 9 there, no problem. That's also a valid tree. Okay? Now, if you keep the 4 and you say put the 9 to the left, you could be talking about something like this. But this is no longer a binary tree, because now there's a node with 3 children. And in a binary tree, you can only have a maximum of 2 children, because you have a binary choice. This is, in my opinion, this is like, you don't need a binary search tree. You can just do a binary tree, or call it a binary tree, because this is a binary decision. Either you're less than or equal to, or you're bigger than. There is no third option here. You know, you're less than or equal to, or you're bigger. That covers everything. So you have a binary choice to make, and therefore you have a maximum of 2 children. If you could do so, let me say this would not be valid. Or at least it's not a valid binary tree, because there's a node now with 3 children. You could do this, and that would be valid. Right? 9 is now to the left of 10. So everything to the left of 10 is smaller. And here 9 is bigger than 4, so it goes to the right of 4, and fine. Make a branch leaf after, or, I mean, this, let's see. Somebody said this, make a branch leaf after 11. Okay, how about this? Is this a valid binary tree? Yeah, so this breaks things. Again, you're okay here, and you're okay here, but you have a problem here, putting 9 to the left of 10. Because now to 10's right, there's a smaller number. So that's a problem. Okay. Good. Okay. If a child node was also 10, where would it go? So yeah, if a child node is also 10, so now we're putting in 10 again. You could put 10 here. Is this a valid binary tree? Yeah, this is fine. The only rule is this one. Okay, everything to the left is less than or equal to, everything to the right is bigger than. By the way, if you like, you can do this. right? Maybe you want the equality to go to the right instead of to the left. It doesn't matter. Just be consistent. Okay. For these lectures, I'll do this. I'll make a preference for the left, but it doesn't matter so long you're consistent. Could there be a case where the sides of the tree connect with each other? No. Not for a binary tree. So there's a couple issues with that. One is that everything goes top down in trees. So you cannot have connections on the same level. Now it's no longer a tree. This is what's called a graph. And you could have such an object. I mean, maybe for some reason, like, it makes sense to connect different parts together. Those things do exist, and there's plenty of problems for them, but it's not a tree. So no, the only connections exist between parents and children. So nodes are only, let's see. I could say, for example, this is getting a little bit off the rails, but this is also not a valid binary tree. Depending on, so the way that this would have to be interpreted, let me go over this again. So here's the different levels of the tree. And here, the parent is skipping having a child. If this were the intent, this is not a binary tree. You can't have nodes. The only edges exist between parent and children. This would be like a parent and like a grandparent relationship. I don't know, like that's weird. But if you were to say, okay, well then this is the level, right? This is level 1, level 0, and level 2. And for whatever reason, this one just looks off. That's okay. But okay. If you put a node 10 to the left of the 11, but to the right of the 4 at level 2. So you're saying, could this happen? No, this should not be allowed to happen. Because equality, you have to make a choice. Either you go left or you go right. So here you've gone right one time, and here you've gone left another time. And so you're not being consistent anymore, and things break if you do this. You could either do this if you want, if 10 gets inserted multiple times. Here it's always equalities go to the right. Or you could have it if equalities go to the left, then it would be like that. Yeah, that's what I mean about being consistent. It doesn't matter, but you must be consistent. All right. How about this tree? Valid or invalid? Valid, okay. Okay, how about this tree? Okay, how about this tree? Very good. Okay, so this is a valid tree. Okay, this is a valid binary tree. Binary search tree, if you like. I'll repeat again because I've had students get confused before in the past. Whenever I say binary tree, I'm using it interchangeably with a binary search tree. Can you have negative numbers in your tree? Sure. You could. You could have imaginary numbers in your tree. In fact, this is a point that we'll come back to. This is actually an interesting thing. We'll be ending foundations here with where we're going. Hash-based indexes and B+ trees. So the whole reason why I'm going through binary trees is so that you have a vocabulary for trees and that you know some of the properties of trees. And a binary tree is like one of the simplest kinds of trees. But SQL and other relational databases use other data structures. One is called a B+ tree, another is called a hash-based index. Once you're comfortable with the idea of a binary tree, it's just a little like tweak here or there to make a B+ tree. So this is why we're going over binary trees now. Relational databases, SQL in particular, uses this data structure. And we're kind of building up to how does this real world database actually store information on like hard drives. And it's actually doing that with a B+ tree or a hash-based index. Don't need to know what these are now. You know, that's what we'll be getting to in the next like week or two. Now, you can do a tree for anything that you can order. So numbers, positive numbers, you can order them. Right here, this question, is this bigger than the thing that I'm looking at? If you can answer that question, that this thing is bigger or this thing is smaller, then you can use a tree. You could even use it with letters, right? Letters of the alphabet. Where it's, you know, where they're at in the alphabet. Do this a little differently. A, P, B, C, F, D. This is also a valid binary tree, where the question is this letter alphabetically before or after it? Doesn't matter. So negative numbers, sure. Letters, why not? I mean, so long it makes sense for that you can say that something comes before or after other things. Okay. I'll keep that, whatever. Okay. Now we will come back to this, and I want you to remember this example, right? That this is a valid tree, okay? That is to say, it can have a really large depth, okay? There's a lot of missing places here for children that don't exist, right? We just like, it's like they're not there yet or something. But they don't have to be for it to be a valid binary tree. Okay, so you can have a tree that's this really long chain. And as I mentioned earlier, you measure arrays by their length, but you measure trees by their depth. And so this tree, the one that goes, all the way down to a billion, that's a tree with a lot of depth. Like the depth is very, very large, close to a billion. And fine. This is a valid tree. Now I'm going to talk about a different kind of tree that has a property to it. Okay, so this is a binary search tree with another property. It is as shallow as the smallest depth possible. Okay? So this is still a binary tree, but it's a binary tree with something else, which is to say that instead of having a tree that's really, really long, it's like you shove the tree and you're squeezing it to be as small in depth as possible. Okay? That is, so for example, does not have this property. And here we'll give one that does have this property. Okay. Now this is still a valid tree, valid binary tree. 1, 2, 3, 4. Okay, that's a valid tree, but it doesn't have this property. One that does is this 3, 2, 1, 4. Okay, and this tree is called a balanced tree, balanced binary tree. Okay, so you can talk about binary trees, and there's certain things that are true about them. Balanced binary trees are also binary trees, but the fact that they're balanced, that they have as small of a depth as possible, is really useful. You can exploit that. You can take advantage of that to do things faster, basically. Okay, let me pause for questions on this concept of a balanced tree versus an unbalanced tree. Or anything else up above. We have like 20 minutes left. And I have 1 or 2 points to make, but we got time for questions. None. Okay. Now, I started off with this example kind of on purpose of what's a balanced tree. Because some people will confuse a balanced tree with what's called a full tree. So let me do a full tree. Okay, that's another example of a balanced tree, number one. But also, let's see, this tree is balanced and full. Okay, that's just some extra vocabulary for you. What a full tree is not really important, but do know what a balanced tree is. The difference being that a full tree has all of its leaves in one layer, and that layer is full. So all of the leaves, like the last layer, is full. So this tree here is missing these. That's why it's not full. Still balanced, but it's just not full because the last layer has some room to go. It's really this that we care about. This is this property of it being balanced. So being balanced is the thing that we actually care about. But for the rest of this lecture, I'm going to work with full trees just to make things a bit easier. Okay, like with some math. And the math isn't too hard, but in any case, again, the only thing that really matters is that the tree is balanced. Being full is, a full tree is also balanced, but a full tree will just make some of the points that I want to make a little bit easier with the math. Okay. I'm going to pick out on a student. How about I don't know. Varun? 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 Sorry, how do you say it?
Varun.
Varun. Perfect. Okay, great. So, we're going to make different examples of full balanced trees. Okay? Boy. Let me start off with. Okay. Is this a full tree?
Yes.
Okay. How about this one?
Yeah, that's full.
Okay. Now, here I'm going to put layer, and then layer number. And here, number of nodes. Okay, so here is layer, wow, what happened there? Okay, here I'm going to label the layers by zeros and ones, if that's okay. Or rather, I'm going to start the first layer with the number 0 instead of 1. So how many nodes are in layer 0?
One node.
One node, okay. How about in layer 2?
2 nodes.
2 nodes, okay. Now, just to kind of save time, just imagine that we can put valid numbers. So I don't have to come up with numbers that work all the time. What is the next full tree? What does it look like?
There's 4 nodes.
4 nodes, okay. Okay, and again, we'll just imagine that we can fill it in with numbers that work. So you just said that has 4 nodes, and that's in layer 2. Okay, how about the next one?
8.
8. Okay. So that is layer 3, and that has 8 nodes. Great. How about the next layer?
Yeah, 16. It keeps going
16.
with powers of 2.
Keeps going powers of 2. Okay, great. Yeah, so great. You've spotted the pattern. So the next one would have 16. That's the last one I'm going to draw because I really don't want to draw 32 little circles. But this is good enough to get the point across. Okay, and as you said, this implies that layer, let's say layer D, or I'll say layer L. Layer L has how many nodes?
2 to the power of layer.
Yeah, 2 to the L. Yeah, 2 to the L nodes.
Yeah.
Okay, perfect. Great, thank you very much, Vernon. Okay, now, if you decide to start your layer with 1, the only thing that changes is that this is no longer true. It's 2 to the L minus 1 nodes. Okay? That's part of the benefit if you like starting it with layer 0, that you don't have to worry about this little minus 1 here. But whatever. Again, these +1, -1 things aren't important unless you work for NASA. Okay. Very good. Now let me pick out on... Okay, I'll pick out on another random student, I guess. Sorry, I see a question. For balanced, you mean both sides have nodes? No. Balanced means that it's as short of a tree as you can possibly make it. Let me give another example of a non-balanced tree, and we'll go through making it balanced. Okay, this tree. This is a valid binary tree, but it is not balanced. So, valid binary tree, and but not balanced. In order to balance the tree, you have to move things around. So, I don't know, using the same numbers. This one is balanced. Because I can take all of these numbers, all of these 5 numbers, and I can make a tree of depth 3. I cannot make a tree of depth 2, because with 2 layers, you can only have a maximum of 3 nodes. After that, you need to add another layer. So this tree is balanced because it's as short as possible. I cannot make it layer 2. This one, to the left, this has 4 layers. And so that's sort of like wasting a layer. There's some layer up above that could be more full. In particular, this, right? Like this whole left subbranch, like the second layer is being underutilized. Layer number 1. Okay? All right. Good question. Yeah, that's the property of being balanced. It's as shallow as possible. The depth is as small as possible. All layers except for the last layer are full. That's another way of thinking about it. The last layer doesn't have to be full, but all of the layers above do have to be full for it to be balanced. Okay? Fine. Okay. So I have 10 minutes left. I want to make a point, and then we'll come back to this next class. Okay. If you don't have an appreciation for or an intuition for the logarithm, I still encourage you to do so. One way of thinking about it is it's the number of digits that are required to represent that number. So if you have a 42 digit, I don't know, let's take this number. 3, 6, 2, 4, 8, 9, 10. Oh, well, okay, sure. 1, 0, 3, 6. Okay? Like this number in decimal. What's the logarithm of this number? Well, if you take base 10 of this number, it's approximately the number of digits. So here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. It's about 10. It's 10 point something, right? I don't know what's after the 10, but it's close enough. It's between 10 and 11, okay? That's always true. For any number in base 10, if you take the logarithm base 10, then it'll be between the number of digits and the number of digits plus 1. So, that's one way to kind of appreciate it. And also the fact that logarithms are so much smaller than the actual numbers. Like it really shrinks things down. Like this is a big number, whatever this number is. 3 billion? Is that right? No, 3 trillion. 3 trillion. And like the logarithm of it is like 10 something. In computer science, they usually use base 2. That's correct. Yeah. But even then, actually, like the difference between log base 10, log base 2, I mean, you're talking about, I don't know. Okay, I gave you an answer. It's like plus maybe 2, plus or minus 2. Plus or minus 3. I mean, it's such a small thing. Even then, it doesn't really matter. But yes, in computer science, and whenever I'm writing log without anything, it's just assumed to be log base 2. That's the same for you. If you write log of some number, I will assume that you mean log base 2. You can write 2 if you like, but you don't have to. Okay. Now, I want to go through this a little bit. 32, 64. And note that, this is 2 to the 0. This is 2 to the 1. This is 2 to the 2. This is 2 to the 3, right? So that's the number of nodes on any particular layer is 2 to the power of that number. Okay? Now there's, binary trees are so much fun. There's other things that you can recognize about this. Like you can learn a lot. And this is like a nice graphical thing to like work with. It's awesome. How many nodes in total are there in the tree? Let me ask this really quickly. For a depth 4 tree, how many nodes in total are there? Now, I mean, on layer 4, we know there's 16. But how about the other ones? You could do the laborious thing and say, okay, well, what's 16 plus 8 plus 4 plus 2 plus 1? You could do that, and you'd get the right answer. But you can do something faster. Notice that this is 16 minus 1. And that's always true. So however many nodes are in the bottom layer, multiply it by 2, subtract 1. That is to say that there's 31 nodes. right? Which is also 16 plus 15. So how many nodes in a tree of depth? I don't know. 943. Yeah, you could write a Python program, right? And then just add them, right? You guys probably know Python enough. You could knock it out in, I don't know, like 10 minutes, let's say. Much faster way. Well, we know that in the very last layer, there's going to be 2 to the 943 nodes in the last layer. In all of the layers above it, there's going to be 20943 minus 1 nodes. So there you go. That's the answer. Now it takes 30 seconds and a calculator instead of you having to like write Python code. You could do that, but this is faster. There's lots of nice properties about this. This is no accident, by the way. I mean, there's... I'll give you kind of a preview for, I don't know, different ways of thinking about this stuff. None of this stuff is going to be like on the homework or a test or anything. But I just think it's cool. And, you know, maybe you like it too. I hope so. I don't know. Another way you could view this number, whatever it is, view it in base 2, right? What would this look like if you were to represent this number in base 2? Well, you'll remember that in base 2, you have a 1's place, you have a 2's place, you have a 4's place, you have an 8 place, you have a 16 place. So for example, the number 5 in binary is 101, right? Because you have 1, 1, you have 0 2's, whatever, this is the 1's place, this is the 2's place, and this is the 4's place, right? So you have 4 plus 1 times 4 plus 0 times 2 plus 1 times 1, right? So you have 1, 4, and 1, 1. That equals 5. So this number means, yes, you do have a node at the top layer. You have 2 nodes in the second layer. You have 4 nodes in the next layer, and the next layer, and the next layer, and this is the number in base 2. What number is that in base 2? 31. If you wanted to write the number 31 in binary, that's it, all ones. How many? 5. So that's kind of cool. Maybe give you a bit of an appreciation for binary numbers. And sometimes it's useful. Like, hey, maybe sometimes you'll find something like, hey, that'll be like a nice little shortcut. And people will be really confused at how you got there. But again, this is not an accident, okay? All of this base 2 stuff, I mean, all of these are because you're working in 2's. And for a full tree, you're maxing out the layers, right? So in this layer, you're going to have a maximum. It's going to be 2 raised to some power. Like, things just keep coming back to 2's here. Okay, I'll leave you with the final point that is the thing that matters, I guess, about the binary tree, or what you should know about a balanced binary tree. It's more true for a full tree, whatever. That is, yeah, I'll keep this here, actually, in binary. I hope this makes sense, actually. In binary, that's this number, all ones. So again, it's because you have 1, 1, you have 1, 2, you have 1, 4, you have 1, 6, and you have 1, 16. Okay, so the other thing that this means is that this is approximately log 2 to the 5. I'm sorry. About 2 to the 5. Yes, right. So this is 2 to the 5 minus 1. 16 minus 16 plus 16 minus 1. Right? Okay, so all of these different ways of looking at this number, these matter because here, that's the number, like 32 is 2 to the 5. You subtract 1. What's the depth of this tree? 1, 2, 3, 4, 5. Okay? So, all of this means that if you have what is the depth of a full tree with 1,024 nodes? That's a question you can ask yourself. Or this is like a practice question. But the reason why this matters is because we'll be, in the next class, we'll talk about using this tree to do a binary search. Okay? We've talked about a binary search on an array, where you go to the middle element and then you throw away half the list, and you can do that. On a binary search tree, that's why it's called a binary search tree, or why people wanted to give it that name, because you can use it for a binary search. Right? You look at the number. Instead of everything here is smaller. So if you're looking for a number that's bigger than 20, you can go to the right. And now you never visit the left end of the tree. And the longest it will take you is the longest path, which is log n. Okay? Okay, so that is, I wanted to get there. That was like the main point of this lecture. And we'll pick it up again next time. Thanks, guys.
I'll go on contested.
Yeah. Let's see, I'm seeing a question here. Does a binary tree just need to have between 0 and 2 nodes from each parent node? Does a binary tree just need to have between 0 and 2 nodes from each parent to be considered binary? Yeah, basically. Yeah. I mean, every node has between 0 and 2 children. Yeah. So this is whatever. I don't know. You're fine with that understanding. I could say more about it. But that's basically true. In my opinion, it's that plus this fact that all of the children to the left are less than, all of the children to the right are greater than. Technically, what you just described with a tree having just between 0 and 2 nodes is what some people call a binary tree, and then a binary search tree is that plus this property. Whatever. I've gone into my opinions on that. Any other questions?
Professor?
Yeah.
Can you just repeat the question that you said at the end? What is the depth of a tree with what?
Oh, what is the depth of a full tree with 1,024 nodes?
Thank you. So what was the final takeaway again? Like, what is it?
Yeah, so the final takeaway is that a binary tree, a balanced binary tree, has a property where you're guaranteed that the depth is at most log n. And that means that you can, and when you do a binary search on a binary tree, it will at most take you log n steps. So here, this tree has 31 nodes, and you can, therefore, it has a depth of 5, and therefore it will take at most 5 steps in order to find any number you want in a tree with 31 nodes.
So a balanced tree has a property which means you're guaranteed a depth of max.
Log n.
What was it? Of 2. Say it again. Of log n.
Log n.
And therefore it will take like max log n.
Yeah, because you start at the top of the tree, and as you search, you go down level by level. And once you reach the leaf, you stop. That's as far as you can go.
Okay,
So-
that makes
Yeah. Yeah, and so it's sort of another perspective on why binary search takes a maximum of log n steps. And
okay. So that's just what we learned before.
yeah, it's just what you learned before, but this is a very kind of graphical way of thinking about it, because yeah, you're thinking about paths through a tree, and how many. I mean, everything is still the same as before. It's just a different perspective.
Okay, thank you.
Yeah. Also, we're talking about binary trees because at some point we'll be talking about B plus trees. And so we have to talk about trees, and you have to, a student should have a concept of what that is, and how trees work and some of their properties. The full binary tree also happens to have, in my opinion, some fun things you can do with it, but
Thank you.
mhm.